Alright, let's dive into the fascinating world of volcanoes, starting with understanding the formation and movement of magma. Magma is a molten mixture of rock, minerals, and gases that forms deep within the Earth's mantle. The composition, temperature, and pressure of magma are crucial factors in determining the type and intensity of volcanic eruptions. Magma forms when the Earth's mantle melts due to various factors like temperature increase, pressure decrease, or the introduction of water. The composition of magma varies depending on the type of rock it originates from, and it generally consists of silicate minerals, dissolved gases like water vapor, carbon dioxide, and sulfur dioxide. Temperature is a key factor in magma formation. Magma temperatures can range anywhere from 700 to 1300 degrees Celsius, 2300 to 2400 degrees Fahrenheit. The viscosity, or the resistance to flow, of magma is directly related to its temperature. As magma cools, it becomes more viscous, which affects its ability to move within the Earth's crust. Pressure also plays a significant role in magma formation and movement. Magma is less dense than the surrounding solid rock, so it tends to rise through the Earth's crust due to buoyancy forces. As magma ascends, the pressure decreases, which can cause dissolved gases to expand and form bubbles. This can lead to an increase in the magma's volume, making it more likely to erupt. So, to sum up, the composition, temperature, and pressure of magma are critical factors that determine the type and intensity of volcanic eruptions. Understanding these factors helps us better comprehend the formation and movement of magma, which is essential for predicting and mitigating the risks associated with volcanic eruptions. Now that we've discussed the formation and movement of magma, let's move on to the role of tectonic plates in volcanic eruptions. The Earth's lithosphere is divided into several large and small tectonic plates that float on the semi-fluid asthenosphere below. These plates are constantly moving, and their interactions play a significant role in the formation of volcanoes and the triggering of eruptions. There are three main types of plate boundaries where volcanic activity can occur: divergent, convergent, and transform boundaries. First, let's talk about divergent boundaries. These occur when two tectonic plates move away from each other, creating a gap between them. As the plates separate, the mantle below rises to fill the void, and the pressure decrease causes it to partially melt, forming magma. This magma then rises to the surface and creates new crust, often forming volcanic activity. An example of this is the Mid-Atlantic Ridge, where the Eurasian and North American plates are moving apart. Next, we have convergent boundaries. This is when two tectonic plates collide with each other. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced to subduct beneath the continental plate. As the subducted plate descends into the mantle, it releases water, which lowers the melting temperature of the surrounding mantle, causing partial melting and the formation of magma. This magma then rises to the surface and forms a chain of volcanoes known as a volcanic arc. An example of this is the Pacific Ring of Fire, which has numerous active volcanoes. Lastly, we have transform boundaries. These occur when two plates slide past each other horizontally. While volcanic activity is less common at transform boundaries, it can still occur if there are zones of weakness or fractures in the crust that allow magma to rise to the surface. A famous example of a transform boundary is the San Andreas Fault in California. In conclusion, tectonic plate movements and interactions such as divergent, convergent, and transform boundaries play a crucial role in the formation of volcanoes and the triggering of eruptions. Understanding these processes helps us comprehend the geological forces that cause volcanic eruptions and better predict their occurrence. Now that we've covered the formation of magma and the role of tectonic plates, let's investigate the different types of volcanic activity. There are three main types of volcanic activity: effusive eruptions, explosive eruptions, and volcanic unrest. Each type is related to the properties of magma and the underlying geological conditions. First, let's discuss effusive eruptions. These eruptions are characterized by the relatively gentle outpouring of lava onto the Earth's surface. Because effusive eruptions typically occur when the magma has a low viscosity, allowing it to flow easily. This low viscosity is usually due to a low silica content and high temperature. An example of an effusive eruption is the eruption of Kilauea in Hawaii, where lava flows slowly and steadily from the volcano. Next, we have explosive eruptions. These eruptions are much more violent than effusive eruptions and involve the rapid release of gas, ash, and rock fragments into the atmosphere. Explosive eruptions are common when the magma has a high viscosity, which can be caused by a high silica content and lower temperature. The high viscosity hinders the escape of dissolved gases, leading to a buildup of pressure that eventually results in a powerful explosive eruption. A well-known example of an explosive eruption is the 1980 eruption of Mount St. Helens in Washington, USA. Lastly, we have volcanic unrest. This term refers to a period of increased activity at a volcano that may or may not lead to an eruption. Volcanic unrest can include increased seismic activity, gas emissions, and ground deformation. These signs indicate that magma is moving beneath the surface, but they don't necessarily mean that an eruption is imminent. Monitoring volcanic unrest is crucial for predicting and mitigating volcanic hazards. In conclusion, the different types of volcanic activity, including effusive eruptions, explosive eruptions, and volcanic unrest, are closely related to the properties of magma and the underlying geological conditions. By understanding these relationships, we can better predict and prepare for volcanic eruptions and their potential impacts. Let's move on to exploring the various volcanic structures, such as stratovolcanoes, shield volcanoes, and calderas. The formation and characteristics of these structures can significantly influence the nature and magnitude of volcanic eruptions. Starting with stratovolcanoes, also known as composite volcanoes. These are steep-sided, conical volcanoes made up of alternating layers of lava, ash, and rock fragments. Stratovolcanoes form from explosive eruptions that produce thick, viscous lava, which doesn't flow far from the vent before solidifying. This leads to the accumulation of material in a cone-shaped structure. Due to their high viscosity magma, stratovolcanoes are often associated with powerful, explosive eruptions. A famous example of a stratovolcano is Mount Fuji in Japan. Next we have shield volcanoes. These volcanoes have a broad, gently sloping profile, resembling a warrior's shield. Shield volcanoes form from effusive eruptions that produce low viscosity basaltic lava. This type of lava can flow long distances before solidifying, creating a wide, dome-like structure. The eruptions of shield volcanoes are generally less explosive than those of stratovolcanoes, but they can still produce large volumes of lava. A well-known example of a shield volcano is Mauna Loa in Hawaii. Finally, let's discuss calderas. Calderas are large, bowl-shaped depressions that form when a volcano collapses into its empty magma chamber after an eruption. This collapse can occur due to the rapid withdrawal of magma during an explosive eruption, or the gradual drainage of magma during an effusive eruption. Calderas can be associated with both explosive and effusive eruptions, depending on the properties of the magma and the geological conditions. A famous example of a caldera is the Yellowstone caldera in Wyoming, USA. In summary, the various volcanic structures, such as stratovolcanoes, shield volcanoes, and calderas, can greatly influence the nature and magnitude of volcanic eruptions. Understanding these structures and their formation helps us better predict and prepare for the potential impacts of volcanic eruptions. Now that we've covered the various aspects of volcanic eruptions, Let's analyze the methods used to monitor and predict them. Monitoring and predicting volcanic eruptions are crucial for hazard mitigation and public safety. There are several techniques employed by scientists to gather valuable information for eruption forecasting, including seismic monitoring, gas measurements, and ground deformation studies. First, let's talk about seismic monitoring. Seismic activity is closely associated with the movement of magma beneath a volcano. As magma rises through the Earth's crust, it generates earthquakes due to the fracturing of rocks and the movement of magma through fissures. By monitoring these earthquakes, scientists can detect changes in volcanic activity and assess the likelihood of an eruption. Seismic monitoring involves the use of seismometers, which record ground vibrations and help identify patterns indicative of an impending eruption. Next, we have gas measurements. As magma rises to the surface, it releases gases like water vapor, carbon dioxide, and sulfur dioxide. By measuring the concentrations of these gases in the atmosphere around a volcano, scientists can gain insight into the movement of magma and the potential for an eruption. Monitoring stations can be set up near a volcano to collect gas samples, or remote sensing techniques like satellite imagery can be used to assess gas emissions over a broader area. Lastly, let's discuss ground deformation studies. As magma accumulates beneath the volcano, it can cause the ground surface to swell or deform. By monitoring these ground deformations, scientists can detect changes in the underlying magma system and assess the likelihood of an eruption. There are several methods used to measure ground deformation, including GPS monitoring, tilt meters, and interferometric synthetic aperture radar. In conclusion, monitoring and predicting volcanic eruptions are essential for hazard mitigation and public safety. Techniques such as seismic monitoring, gas measurements, and ground deformation studies provide valuable information for eruption forecasting. By understanding and utilizing these methods, scientists can better anticipate volcanic activity and help communities prepare for and respond to the threats posed by volcanic eruptions.